All right, there are two more examples for empirical formula, and they're harder than the last example in the last section that we looked at, and that's why they're in their own separate section. We'll start with the first one. This is a sample of vitamin C, 0.1247 grams of it, and it contains 0.0510 grams carbon, 0.0057 grams hydrogen, 0.0680 grams of oxygen. What's the empirical formula? And then the molar mass is 176. What is the molecular formula? All right, so we're going to use the same technique again. We're going to take our quantities of carbon, hydrogen, and oxygen, convert them to moles, take the ratio, or rather divide by the smallest number of moles, and then we'll have hopefully the simplest formula. I might have to manipulate it a little bit, but we'll get there. Okay, so we have 0.0510 grams of carbon, 0.0057 grams of hydrogen, 0.0680 grams of oxygen, 12.011 grams per mole for carbon, 1.008 grams per mole for hydrogen, 16 grams per mole for oxygen, and we end up with 0.00425 moles of carbon, 0.0056 moles of hydrogen, and 0.00425 moles of oxygen. Okay, so now we have our moles. We can take ratios. I like to set it up this way. You don't have to do it this way. You could just take these numbers and divide by the smallest number. Just do it as in a column or something, but I like to do it this way. So this is going to be a ratio of moles, not a ratio of masses. Divide by the smallest number. To get C1, H1.3, and O1. All right, that you could argue that's the empirical formula, but you really want whole numbers for it. So you're going to multiply times whole numbers, integers, to see how close you can get to a set of integer values. So if you multiplied times 2, you'd have C2, H2.6, O2, and 2.6 really isn't close enough for rounding. So we'll instead multiply times 3. Let's see what we get there. C3, H3.9, O3. So that's close enough. We can say that the simplest ratio then would be C3, H4, O3. Now, if that were no good and you wanted to keep going, multiply times 4, 5, 6, you can do that. You can just keep going until you find some number which gives you whole numbers or integer values for all of them. And of course, you could multiply times 10. In this case, you'd have C10, H13, O10, but that's not the simplest ratio. So you have to be careful with that. So this then is the empirical formula, and the next step is to figure out the molecular formula, given that the molar mass was, that's part B there, the molar mass was 176. So part B here, what is the molecular formula if the molar mass is 176 grams per mole? Question mark. So remember, it's the molar mass divided by the empirical formula mass to get the ratio, which would be the number you're going to multiply the integers in the empirical formula by to get the molecular formula. So you want to get the empirical formula mass first. This is going to be 3 times 12.001 plus 4 times 1.008 plus 3 times 16. The empirical formula mass is 88.07. Then you want to take a ratio of the molar mass to the empirical formula mass. So this is going to be 176 divided by 88, and that is going to be equal to 2. So that tells us that we want to take our empirical formula of C3H4O3 and divide it by 2 to get the, multiply times 2 to get the molecular formula, C6H8O6. So that's the molecular formula for vitamin C. All right, now coincidentally, in our very first example in the last video for empirical formula, the multiplier was 2 as well. There's nothing magic about that. My examples, for some reason, all turn out to be 2, but they could be any number, 1, 2, 3, 4, like that. All right, so just for fun, I thought I'd draw the structure of vitamin C for you. And bear with me here. It's a 5-membered ring, and I'm going to explain it to you. Let me draw it first. Hopefully I got that right. You're going to learn all about these structures in a few chapters down the road. You'll be able to say quite a bit about this structure later. But anyway, one of the things I want to show you is that each group of electrons there, so the single bond has two electrons in it. The double bond has 4 electrons in it. This is a lone pair. There's 2 electrons here, 2 electrons here. So each carbon wants 2, 4, 6, 8. 2, 4, 6, 8. That's the octet rule. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. So that's either with double bonds or single bonds. However, you know, it ends up 8 is the number. Oxygen has 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. Like that. Hydrogens only want 2. So later on, never ever try to make more than 1 bond to hydrogen. So let's see if our structural formula matches the molecular formula here. Okay, so C6, 1, 2, 3, 4, 5, 6. Hydrogen is 1, 2, 3, 4, 5, 6, 7, 8. Right here, 8. And then oxygen is 1, 2, 3, 4, 5, 6. So O6. So it does match. That's a pretty complicated looking formula, but actually I'm a little bit under the weather today, and I took some vitamin C this morning. So I have, I consumed some of this today. And let's see what else to say about it. Vitamin C. Yep, I guess that's it. All right, we'll move on to the next slide. And this one is going to introduce you to the third empirical formula problem that we are considering here. So, the technique here is to take your unknown compound like the vitamin C in the last example, so just some solid organic compound, let's say. And we want to figure out how much carbon, hydrogen, and oxygen it has in it. And so this is kind of a bare bones method It's more sophisticated today, but this is the basic process that's going on during in order to determine the amount of carbon, hydrogen, and oxygen in a substance. So you take your solid here, then you're going to heat it in the presence of oxygen. This is an example of a combustion reaction, which we'll talk about. And the organic molecule will burn in the presence of oxygen. The products of the reaction are CO2 and water. So that's a typical combustion reaction. This material is an absorber for water. So it's some graphite type material. And then this one, I don't know exactly what they are. There's all kinds of different materials, but this red one here would be the absorber for CO2. So the mixture of CO2 and water products come through this region. The water is absorbed, and then the CO2 continues along and it gets absorbed here. So you can disconnect here and here. You can weigh the tube with the absorber in it before, and then after, when the water is contained within, same thing here, and by difference you can get the amount of water and CO2. So the technique that we'll use for the last example is to figure out how you can go from mass of water to moles of water. So mass of water you get from the experiment. If you know it, you can go to moles of water. Then you can go to moles of hydrogen, okay? And from that, using molar mass, it's 2 times as many moles of hydrogen as there are water. Then you can use the molar mass for hydrogen to get to the mass of hydrogen. Similarly, for the mass of CO2 that you get, you can figure out how many moles of CO2 that corresponds to. Then you can figure out how many moles of carbon that are present, and you can get your grams of carbon using molar mass. All right, now here is your unknown sample right here. It's actually here, and it contains carbon, hydrogen, and oxygen only. And so if you want to get the amount of oxygen contained in the unknown, you have to do it by difference. So you're going to take the mass of your unknown, subtract the mass of the hydrogen, and subtract the mass of carbon, and that'll give you the mass of oxygen. The reason why you cannot get the mass of oxygen from the water and the CO2 is that some of the oxygen in the water that's formed and in the CO2 that's formed comes from the oxygen that's blowing through and performing the combustion. So the amount of oxygen here added together does not equal the amount of oxygen in the sample. It equals the amount of oxygen in the sample and in the oxygen that's flowing through for the combustion. So you don't want that. You want the mass of oxygen that's in the compound in order to get the empirical formula of the compound. So the technique then to get the mass of the oxygen is to take the mass of the unknown, which contains carbon, hydrogen, and oxygen, and you're going to subtract the mass of the hydrogen plus the mass of the carbon. Or you could say you're going to subtract the mass of the hydrogen and subtract the mass of the carbon. Okay, once you have the mass of the oxygen, then you can go to moles of oxygen using molar mass. Then you'll have moles of oxygen, moles of hydrogen, and moles of carbon, and then you can set it up CHO with the moles as the subscripts, divide by the smallest number, and determine the empirical formula for it. Okay, so this is kind of complicated here, but this is typically what's done in the laboratory if you want to get your empirical formula. Okay, so then let's go ahead and do it on the next slide. So combustion analysis, 1.01 grams of the unknown compound, which contains carbon, hydrogen, and oxygen only. was combusted in the presence of excess oxygen to produce 2.955 grams of CO2 and 0.5190 grams of water. What is the empirical formula? And then given the molar mass is 212, what's the molecular formula? All right, so we're going to take our 2.955 grams of CO2 and our 0.519 grams of water, and we're going to get the carbon and the hydrogen from these, not the oxygen. So we're going to go to moles of CO2. Molar mass of CO2 is 44.01 grams per mole of CO2. Okay, then we want to go to moles of carbon from moles of CO2. If you look at the formula, there's 1 mole of carbon for every 1 mole of CO2. That'll give us moles of carbon after everything cancels. We can stop there and calculate the moles of CO2. So let's go ahead and do that. Let me get my notes here. This is going to be 0.0671 moles of carbon. Then we can continue here and say 0.067 moles of carbon times 12.01 grams per mole of carbon, and that'll be equal to 0.8066 grams of carbon. All right, I like to color code here. I'm going to put my moles in green and my masses in red. And I recommend that you do something like this so that you don't confuse them. In the end, you're going to have moles for carbon, hydrogen, oxygen, mass for carbon, hydrogen, and oxygen. You got 6 numbers on your paper, and it's very easy to switch them to, mix them up, pick one for the other, and so on. Okay, let me just bump that down. Oh, it's not going to let me do that. There we go. Whoops. All right, actually, I'm going to move this down. 0.5190 grams of water. Okay, so we're going to do the same thing. We're going to get the hydrogen. So you go from grams to moles. There's 18.02 grams of water per mole of water. That's the molar mass. Now here's where you compare up to carbon. In this case, you look at the formula, there's 2 moles of hydrogen for every 1 mole of water. Okay, stop here and calculate your moles of hydrogen, which is going to be 0.0576 moles of hydrogen. Put your moles in green. Then you can take those moles and you can convert to grams. Whoops. 0.0576 moles of hydrogen, and then 1.008 grams per mole of hydrogen. So this one is 0.0582 grams of hydrogen. Put your mass in red. All right, now you have to do the subtraction, and you're going to take, let's see, our original amount is right here. Whoops, right here. So that's the amount of the unknown containing carbon, hydrogen, oxygen. We have the mass of carbon and the mass of hydrogen. We're going to subtract to get the mass of oxygen out of the unknown. So you want to get your mass of oxygen here by taking 1.018 grams of the unknown, and you're going to subtract 0.8066 grams of carbon. subtract 0.0582 grams of hydrogen, and then the mass of oxygen will be equal to, let's see, we have 0.1532 grams of oxygen. So put that in red, that's the mass of the oxygen. Next we want to go to moles because we want mole ratios. So you say 0.1532 grams of oxygen and